In example 3, we consider the graph of f of x equals 2 to the x. That's going to be our parent function. And we have a sketch of it here. And then I listed the order pairs that we used when we graphed this earlier in the notes. And in example 3, what we're going to do is look at various transformations of this parent function, this exponential function, and using the concepts we learned back in chapter 2 that apply to any function. So first we're going to look at g of x, which is 2 raised to the x plus third power. So here we're replacing x with x plus 3. When we do that, the transformation that we have is that the function is shifted left 3 units relative to the parent function. So if it's left 3, what we would really do is we're going to subtract 3 from all x values. So since this is just one transformation, what I'm going to do is I'm going to plot the points on the parent function, and then I'm just going to move each one of those points left 3 units. So I'm going to do 1 square is 1 unit. So I'll put the scale on. I'll just denote it on the increments of 5. And now I'm going to go ahead and plot those points on the parent function. So I have -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. And once again, I'm getting those points from this table here, or just substituting in the values of x in the function 2 to the x. And then g of x, I'll plot that in red. I'm going to find the new points by moving all of these points that I just plotted left 3. So I'm going to take 3, 8 and move it left 3. It's going to become 0, 8. And I'm going to do the same thing for every other point. So I'm going to move them all left 3. So 1, 2, 3. So 2, 4 becomes -1, 4. 1, 2 becomes -2, 2. 0, 1 becomes -3, 1. And then I'm going to plot the last 2 as well. And then I'm going to connect these with a nice smooth curve. And so this function right here is our transform function, where the graph is shifted left 3 relative to the parent. The parent function, I'll just dash that function in. So the blue function is f of x is 2 to the x. Let's take a look at our next function. So in letter B, we're looking at h of x, which is 3 times 2 to the x. So what's happening here is we have this 3 that's multiplying the entire function. So the transformation in this case is a vertical stretch by a factor of 3. And what that does in terms of all of our points is it multiplies y values times 3. Nothing is happening to the x values. So just like when we plotted g of x, I'm going to plot those points on the parent function, and then I'm going to multiply all the y values by 3. So here are the points on the parent function. I'll do those in blue. So 0, 1, 1, 2, 2, 4, 3, 8, -1, 1/2, -2, 1/4. And now I'll plot h of x in green, and I'll multiply all those y values by 3. So I can't do 8 times 3 is 24. That's not going to fit. 4 times 3 is 12, so I'll just approximate that. So I'll have 2, 12. 1, 2 becomes 1, 6. 0, 1 becomes 1, 3. -1, 1/2 becomes -1, 3/2. And -2, 1/4 becomes -2, 3/4. And now I will go ahead and connect these with a nice smooth curve. This will be our function h of x, which is 3 times 2 to the x. And y equals 2 to the x, I have those points here. I will go ahead and sketch that with a dashed line because that's our parent function. So this is f of x is 2 to the x. Let's take a look at the information in this box here. So here it says, if we think of the exponential function of the form y equals a times b to the x, what does the a tell us? So we just saw that a is the vertical stretch factor, right? So on these functions, in h of x, we see when a is 3, we had a y-intercept of 0, 3, and that's going to be the case for any exponential function of this form. So the a value tells us the starting, or sometimes it's called initial value, which is the y value when x is 0. So the y-intercept is 0, comma a, rather than 0, comma 1 for the parent function, which is for y equals b to the x. And that's going to become useful when we do application problems coming up. Okay, the next function that we have is k of x, and k of x is negative 2 to the x. So what does this negative do outside the function? That negative is it's going to reflect. It's going to be a reflection over the x-axis, and numerically that means we're going to multiply y values by -1. So I'm going to go ahead again. I'm going to plot the points on the parent function quickly, and then I will reflect all those points over the x-axis, and we'll see what we get. So here are the points on the parent function. So -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8. And then we're going to reflect all these points over the x-axis. So it's instead of -2, 1/4, it's -2, -1/4, -1, 1/2, -1, -1/2. 0, 1 becomes 0, -1, 2, 1, 2 becomes 1, -2, 2, 4 becomes 2, -4, and 3, 8 becomes 3, -8. And then we're going to go ahead and connect these with a nice smooth curve. And so this is h of x, which is the opposite of 2 to the x, and I will go ahead and sketch in the parent function as well with a dashed line, because that's not really the function that we're plotting. Last one we're going to take a look at is m of x here. So m of x is 2 to the -x plus 1. So what transformations do we have? Firstly, we have a negative x instead of positive x. So when we have that, that is a reflection in the y-axis. So we're multiplying x values by -1. And the other thing that we have is this plus 1 outside of the function, and that is a shift up 1 unit. So that means we add 1 to y values. Okay, we're going to do the same approach here. We'll plot the points on the parent function, and then we will reflect. So we'll multiply all the x values by -1, reflect those in the y-axis, and then we will shift those points up 1. So here we go again. So -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8. Those are the points on the parent function. And now let's plot the points. I'll make m of x red. So I'm going to take each y value and reflect it over the x-axis and then go up 1. So 3, 8 is going to go to -3, 8 and then move up 1. So that's going to be -3, 9. 2, 4 is going to be reflected to become, so I'm starting with 2, 4. That's reflected to become -2, 4, and then it'll go up 1. So it'll be -2, 5. And then let's do the next one. So we've got 1, 2. It's going to be reflected over the y-axis. It'll become negative 1, 2, and then up 1. So it's going to be negative 1, 3. 0, 1 reflected over the y-axis is still going to be at 0, 1. So let me get this point, 0, 1. It's still going to be there, but then it moves up 1. So it goes from 0, 1, reflected, still 0, 1, up 1. So it's going to be 0, 2. And then we have negative 1, 1 half. So negative 1, 1 half, it's going to be reflected. Let me make the point blue. It's going to be reflected over the y-axis, so it's going to become positive 1, 1 half, and then up 1. So it'll be positive 1, 3 halves. And the last point that we have is negative 2, 1 quarter. That'll become positive 2, 1 quarter, and then up 1. So it'll be positive 2, 5 quarters. And then I'm going to connect these with a nice smooth curve. So we're going to have something like this. And if we wanted to, I could show all these points analytically as well. So I'll do that here for you. So if you don't like the way we did it geometrically, we can have y, or graphically, y equals 2 to the x. So these were the points we did. Negative 2, 1 quarter, negative 1, 1 half, 0, 1, 1, 2, 2, 4, 3, 8. And what we did was we multiplied x times negative 1 and y plus 1, and then we got all of our new points. So I'll squeeze those in here. So we have x and then m of x. So let's see what those points are. So we're going to multiply all the x's by negative 1. So that's going to be 2, 1, 0, negative 1, negative 2, negative 3. And then the y values are going to be adding 1 to them. So it's going to be 5 quarters, 3 halves, 2, 3, 5, 9. And those are the points we plotted. So if you like this more numerical approach, you can do that as well. One thing to note here is previously we had a horizontal asymptote on these graphs at y equals 0. But since this graph is shifted up 1, our horizontal asymptote, I'm going to go ahead and sketch that, on this graph is at y equals 1.